Hello learners, welcome to this video lecture on wind energy, module 4 of energy engineering, presented by myself Ranjit BK, Assistant Professor, Department of Mechanical Engineering, Global Academy of Technology. In this video lecture, we understand the concepts of wind energy, that is the properties of wind, then the availability of wind energy in India, the wind velocity, the power from the wind, how it can be extracted, then the major problems associated with the wind power, then we understand the various types of wind machines, their characteristics, and then we understand the coefficient of performance evaluation using numericals. So let's begin learning. Wind energy is rightfully an indirect form of solar energy. It is said that it is an indirect form because it is induced, the wind movement is induced chiefly by the uneven heating of the Earth's crust by the sun, and there are few irregularities on the Earth's surface and the rotation of the Earth. So combined effect of all this is the movement of the air or the blowing of the wind. So the conversion of the kinetic energy, that is the energy of motion of the wind, into the mechanical energy is usually used to perform any useful work or predominantly to generate electricity. So these devices which convert the wind energy are known as wind turbines. If you look at the potential, India has a good potential of generation of wind energy. It is estimated that India can produce about 20,000 megawatts through the wind energy, and due to its potential, it forms that it is one of the promising countries for tapping this resource, and it has our country has progressed in this direction. So, as on September 2020, the total installed wind capacity was roughly about 38 gigawatts. We stand fourth largest in terms of installed wind capacity when compared to the other countries. So, in order to understand how does a wind turbine work, quick video for a better understanding.
How does a wind turbine work? You've probably seen a wind farm. But do you know how wind force is converted into electrical energy? We are going to show you how a wind turbine works. Each wind turbine has a wind vane at the top that indicates the wind direction. This allows the turbine to rotate on the tower and face the wind. The blades also rotate on their axis for maximum resistance. Wind force, that is, the kinetic energy contained in moving air currents, spins the blades. These are designed to fully capture its energy. They can be as long as 60 meters each and are made of very light and resistant materials for ease of movement. This is why they can produce energy even with very light winds, starting from about 11 kilometers per hour. With very strong winds, above 90 kilometers per hour, the blades are placed in the feathered position and the turbine stops spinning for safety reasons. The blades are attached to the wind turbine through the hub, which is coupled to the low-speed shaft. The low-speed shaft is given this name because it spins at the same speed of the blades, between 7 and 12 revolutions per minute. To produce electricity, it is necessary to increase the turning speed of the low-speed shaft. That is the mission of the gearbox, which raises the speed over 100 times and transfers it to the high-speed shaft. The high-speed shaft, that rotates at up to 1500 revolutions per minute, is connected to a generator. The generator converts the kinetic energy into electricity, a source of energy that is easier to transport and use. The electricity produced in the generator is conducted through the interior of the tower to the base. There, a transformer raises the voltage for transport inside the wind farm. From each turbine, alternating current is sent to the substation through underground cables. Here, the voltage is increased again to feed it into the power grid and transport it to end consumers. This is how we use the wind to light cities, feed industries, schools or hospitals, or operate our household appliances in a clean and sustainable way.
So the video went on to show how the turbine is usually made of, and it how it consists of a gear mechanism, which when the wind blows, the wind speed is converted into rotary motion, and the speed is increased through a gear mechanism, and then the power that is generated is transmitted. So, a quick recap: the power that is generated is then supplied and transported using the grid system. If you look at the power output from the wind, it is usually dependent on the wind speed and the cross section, that is the wind swept by the rotor, and the overall conversion efficiency. And this output is computed using the expression P, that is power generated, is equal to half rho A V cube. And the rho stands for density of the air, A stands for the cross section of the area that is wind passes through, and V is the velocity through which the wind blows. And if you look at this expression, the rho and A being the constant, the wind or the wind power that is produced is thus proportional to the cube of the wind velocity. So power is directly proportional to cube of the wind velocity. There are various types of wind turbines that are used. The classification is based on the axis of rotor. It could be either a horizontal axis or a vertical axis. In a horizontal machine, the axis of rotation is horizontal, and in case of vertical machine, it is a vertical. Then, according to the size, it could be either a small scale, usually up to 2 kilowatts. So, this is usually used for remote applications. Medium sized machines are used for supplying electricity at small individual clustered homes and local use, and large scale, greater than 100 kilowatt, used to usually distribute or generate power into power grids. The next classification is based on the output that it is producing. It could be either a DC output, where the power generated by the wind machine is in the form of a DC power, or it could be an AC output. Within AC, it could be either through variable frequency or constant frequency. But more or less, these wind type of wind machines are AC output machines. Then, according to the rotational speed, it could be either a constant speed with pitch blades being varied, and it could be nearly constant, or it could vary the speed. So, there are three permutations possible. However, it is the third category is predominantly found to be used. So, if you look at the horizontal axis machines, the evolution has taken from this end to this end to what or where we are today. Right from the Dutch type, which used materials, different available materials at that point of time, to one blade, then to two blades, and in fact now we have progressed to three blades. So, and we all typical wind turbine mill has a three blade mechanism. In addition to this movement of or production of energy from the wind, there is something called a yawing mechanism. So, what happens is there is a sensor which senses the movement of the air, and as the movement and direction of the air. So, wherever the direction of the air is tend to be more, the uh, turbine hub orients itself to the direction of the wind that it is blowing. So this is basically known as a yawing mechanism, and by default all turbines are designed to have a yawing mechanism so that the maximum amount of energy can be extracted. In case of a vertical machines, it is either a 7S rotor or a derailleur rotor, with the 7S rotor being represented here and the derailleurs. So the vertical axis has its own set of problems and is usually not employed anywhere, and the horizontal ones are the one which is predominantly used. The technology has advanced further. Very soon, we are going to see bladeless turbines. So, if you imagine what is a bladeless turbine, you can look at this. That is, in a nutshell, the research is progressing further. And why three blades? Why we have progressed to three blades and we have stopped, and why not we have grown more? There is this explanation available.
People have been harnessing the power of the wind for thousands of years. The earliest recorded evidence of this can be seen over 1,000 years ago in Persia. But these machines have evolved from simple devices used to crush grain and pump water, to towering monsters generating enough electricity to power entire towns. Traditional wind turbines come in many shapes and designs, but they have all given way to a fairly consistent three-blade design. Today we're going to answer the question, why do wind turbines have three blades? We can imagine each blade as a wrench tightening a nut. If we increase the length of the wrench, we can generate more torque. That's the force that causes rotation. Likewise, if we add a second wrench, we can apply even more force. The same principle applies to wind turbines. So naturally, you may think, why not add as many blades and make them as long as possible? The biggest wind turbine has a diameter of 164 meters. Each blade weighs 33 tons and each costs hundreds of thousands of dollars to manufacture. So more blades equals more weight and more cost. So maybe less blades is better? Let's compare our standard 3-blade design to its immediate competitors, a 2-blade turbine and a 4-blade turbine. Let's assume they have the same blade design for now. We can easily eliminate the 4-blade design with a quick cost analysis. Each of these blades costs a lot of money. Adding a 4th blade provides such a marginal increase in performance that it does not justify the additional cost. So it's down to 2 and 3 blades. A 2-bladed design can match the performance of a 3-bladed design by increasing the chord of the blade by 50%, which eliminates the cost advantage, so it's pointless. Or we can increase the rotational speed by 22.5%. Turbines with 2 blades will spin faster in the same wind, due to the reduced drag they experience, but spinning faster is a negative. Let's explore why. A faster spinning blade will generate more noise. This is what a wind turbine sounds like up close. Yeah, people don't like living next to these things, so we need to minimize the noise they make by minimizing their speed. Next, we need to worry about centrifugal force. As the blades spin faster, their apparent weight increases. Thus, the central hub and the blades need to be stronger to resist the additional stress. Again, this adds cost. This is what can happen when a wind turbine's brakes fail in strong winds. So a 3-blade design can generate more power at slower rotational speeds than a 2-blade design, while being more cost efficient than a 4-bladed option. So the 3-bladed design is our Goldilocks choice, not too much and not too little.
The summary of the video, which went on to explain why the optimum number of blades are fixed as 3. So it has got to do with more power being generated at lesser speed and the noise that is predominantly eliminated. There is an expression usually available for evaluating the coefficient of performance. So it basically what it does is it equates the energy and the wind velocity with the pressure difference, and and finally after all the substitution and deduction, it comes to the expression that the power that is available becomes maximum at certain stage, and this is 0.595 the total power. So if this is the total power that is available, the maximum power is only 0.595 times the total power. So this gives rise to the factor of coefficient of performance, which is proportion to the power of the wind that the rotor can extract. So there is a this maximum value is known as Bett's coefficient, that is this 0.595. So any windmill cannot be more efficient than 59%. So the theoretical limitation is this. So no turbines can be efficient greater than 59%. So few problems which are associated with the wind power. It is the location of the site. The site must be large enough with reasonable wind velocity, otherwise it may end up not producing any energy at all. And the variation, so wind velocity varies with time and varies in direction as well also, and it varies as the cross section of the wind turbine changes. And if there is variation in this wind that is blowing, it it tends to cause fatigue in the blades, and this needs to be taken care of. And there is no storage system. There is absolute necessity of storing this power. So what essentially now it is happening is, as the wind blows, the energy is transformed, and the energy is converted and then transformed into further usage, and there is no storage. So the another problem is the strong supporting structures. So there is a good need of a strong supporting structure, since these turbines are located at a certain height. The supporting structure should be ensured and designed in such a way that it should be able to take the wind impact, and this usually adds to the cost of the windmill. Then it occupies large areas of the land, and the land is unavailable due to other use, and it has to be protected in order to avoid any accidents. Then nature of the ground surface should be very stable. Erosion should not exist, as it could possibly later at point of time it could wash out the foundation, and it could end up destroying the whole windmill setup. Then the availability of the wind, it is not same, it is not even at all places. So it has to be ensured that the wind should be available every time, or at least to the maximum possible time, and studies are usually conducted before this wind turbine is installed. If you like the content, please consider subscribing to the channel and hit the bell icon for getting the further updates. So we move on to the numericals. In order to solve the numericals and to evaluate the coefficient of performance, we make use of these numericals, these formulas that are to be implemented for solving them. The first one is density. Rho is given by P by RT. Then the total power in the wind stream given as P total is equal to rho A VI cube by 2 GC. Then total power density given by total power divided by area in terms of watt per meter square, and maximum power is 8 rho A VI cube by 27 GC, and maximum power density again maximum power divided by the area expressed in watt per meter square, and possible power density is power density into the efficiency, and this power density has to be from this P total, and at any cost it should not be taken from maximum power density. This has to be noted. And the total power is possible power density into area expressed in terms of watts. And sometimes also the torque is required to be evaluated, given by the expression 2 by 27 GC rho d VI cube by N, where D stands for the blade diameter, and the speed, turbine speed, should be taken in seconds. Please be very careful. The usual notation is rotation per minute, but here while substituting, N has to be in RPS. And there is this axial thrust that is produced in the turbine blades, evaluated by the expression pi by 9 GC rho d square VI square. So essentially this slide gives you all the formulas that are required to solve the wind turbine numericals. So please ensure that you are well versed with the formulas in order to solve them better. So we look at the sample numericals. There is a wind velocity at a place at 18 meters per second, and the temperature and pressure are given. We need to determine the total power density, the maximum power density, and the possible power density, along with evaluating the total power, torque, and the axial thrust. Further, the data given is turbine diameter is 125 meter and turbine speed is 42 rpm, and the conversion efficiency is 35%. So we look at how do we solve this. So air density is calculated as P by RT. P is given as 1 atmospheric pressure, and T temperature is 15 degrees Celsius converted into the Kelvin and substituted, and found that the density is 1.226 kg per meter cube. The total power density is given by the expression rho VI cube by 2 GC, where VI is the velocity that is given 18 meters per second. So when you substitute the values, you end up getting 3575 watt per meter square. Then the possible power density is power density into efficiency. The conversion efficiency given as 35%. So it is 1251 watt per meter square. Then the total power is nothing but the possible power density into area. So this 1251 multiplied by area is pi d square by 4. Diameter is given, turbine diameter. So you end up calculating the power. So the power that is generated by the wind turbine is 15.3 megawatt. Then the torque that is produced given by this expression 2 by 27 GC rho d VI cube by N, which is transforming to 94.5 kilonewton, and the axial thrust that is produced is 2166 kilonewton. This GC is to be noted that the GC carries a value of 1. So a similar numerical, the velocity is 15 meters per second, where the temperature is 15 degrees and 1 atmospheric. We need to determine these parameters given that the turbine diameter is 120 meter and speed 40 rpm. You should be noted here that there is no conversion efficiency given, so you are free to choose or assume a suitable conversion efficiency. Since it is not given here, it is assumed as 35% and the numerical is completed. So same as usual, the density is calculated by P by RT. P at 1 atmospheric and temperature is 15 degrees Celsius, so converted into Kelvin 1.226 kg per meter cube, and then the power density given by rho VI cube by 2 GC, where VI is 15 meters per second, that is the given data. So you end up getting the power density as 2068 watt per meter square. Then the possible power density is power density into the conversion efficiency. As I said earlier, the efficiency value is not provided, hence it is to be assumed as 35%. Then the total power is nothing but possible power density into the area. So the total power that is generated is 8184 kilowatt. Then the torque produced rho d VI cube by N into 2 by 27 GC, where d is the diameter of the turbine, 120 meter, and N is given in RPM, which is substituted in RPS and obtained as 55.17 kilonewton. So it is just a direct substitution. The trouble here is remembering these formulas, so please be well versed with this and solve the numericals. The axial thrust given by pi by 9 GC rho d square VI square, that is 1385.8 kilonewton, and